In this video, we're going to introduce the concept of calculus, specifically derivatives and integrals, and have a look at what they are and why they're so important in the courses that you're going to be studying. So first of all, let's discuss why it's so important to study calculus and what calculus is. Well, calculus is concerned with studying two different things, so there's two branches of calculus. The first is interested in finding slopes, and that's a problem from the 1600s. This relates to instantaneous rates of change. The second branch, even though you typically study it later in your study of calculus, is actually an older problem concerned with finding areas under curves, and that problem is 2,500 years old. That actually denotes the total change that occurs. And why we might be interested in studying this? Well, for example, we might want to know the rate of change of a population with respect to time. That would have to do with slopes. Or if we had information about the rate of change of a population with respect to time, we might be interested in figuring out the total change in that population that's expected to occur in a given time interval. As far as the process by which we're going to solve both of these problems, what we're actually doing to figure out the information that we need is approximating it by finding things that we already know and then trying to make the approximation better. That's illustrated in the two figures at the bottom of the screen, and we're actually going to go into that in more detail in the following slides so that we understand what they represent a lot better. So first of all, let's start with the problem of finding slopes, and let's look at what we already know. From high school, you already know how to find the average rate of change. In other words, how to find the slope, which is rise over run. So that's a concept that you learned in your high school days. And all it denotes is we have to figure out the vertical change and the horizontal change. And so the vertical change is your rise, the horizontal change is your run, and you simply divide the vertical change by the horizontal change in order to figure out the slope. The line that passes through 2 points on the curve is called a secant line, and so what we've done is we found the slope of the secant line through these points. Now let's have a look at what we want to learn. We want to find the instantaneous rate of change at a particular point. So for example, rather than trying to figure out the average speed of a car in its journey from 5 p.m. to 6 p.m., we're talking about finding the instantaneous rate of change, so the instantaneous speed of the car at 5:21 p.m. for instance. In order to do that, you're trying to find the slope at 1 point on a curve. So here's the problem. We know that to find slope, you need 2 points on a curve, but we're interested in finding slope at just 1 point, as indicated in the figure. Well, what we're looking for here is the slope of a tangent line. So a tangent line is a line that touches a curve at a point and has a slope equal to that of the curve at that point. So again, what we know is how to find the slope of a secant line, a line through 2 points. What we want to find is how to find the slope of a tangent line, a line touching the curve at 1 point and having the same slope as the curve there. So how would we do this? Well, let's consider what we know and what we want. We know how to find the slope if we have 2 points, but we want to find the slope at 1 point. So let's try to figure this out graphically. What we can do is start with 2 points, because that's the only way that we know how to find slope. So let's consider this figure on the left. We're starting with 2 points, P1 and P2, and we want to find the slope at P1. So first of all, here the curve that we're trying to find the slope of is illustrated in red, so it's our parabola. And what we have is the secant line shown in blue through the 2 points, P1 and P2. And what we want is the tangent line shown in green, so let me just label these. And so that's the tangent line at P1. So again, we want to find the slope of the green line, the tangent, but all we know how to do is find the slope of the blue line, the secant. So here's the idea. What we want is the slope at just P1. So let's consider what happens as we bring that second point, P2, closer and closer to P1. So it pretty much looks like we're dealing with only 1 point. So what happens as we do this? Well, let's have a look at the figure on the right. As we bring P2 closer to P1, you can imagine that the slope of the secant line in blue is going to get closer and closer to the slope of the tangent line in green. So in the diagram on the right, we see that P1 and P2 are much closer together, and indeed, the slope of the blue line, the secant line, is much closer to the slope of the green line, the tangent line. So the idea would then be to bring P2 as close as possible to P1 and consider what happens as you do that. So now let's consider this same problem numerically. Let's go ahead and make a table of values, figuring out the slope of the secant as we bring P2 closer and closer to P1. And remember, P1 is the point x equals 1, and that's where we're interested in finding the slope of the tangent line. So does the slope of the secant seem to approach a particular value? So first, let's consider the table on the left. What we're doing here is starting with the point P2 to the left of the point P1. So at first, we start with P2 equal to 0. Well, if P2 is at 0, it's quite far away from P1 at 1, and so the slope isn't going to be a very good approximation to the tangent, and indeed we find a slope of 1. But now, what happens as we bring P2 closer and closer to P1 from the left? You'll see that the slope seems to approach a value of 2. Now let's try the same exercise, but starting with P2 to the right of P1. So in the table on the right, we start with P2 at x equals 2. Again, it's quite far from P1, which is at x equals 1, and we get a slope of 3 initially. But now let's bring P2 closer and closer to P1 from the right. Well, the slope then gets closer and closer to 2. So looking at what happens when we bring P2 closer and closer to P1, both from the left and from the right, we seem to have a slope of 2 that we're approaching. So that means the tangent has a slope of 2. So did we find what we wanted? Yes, because we were after the slope at a particular point, so at P1, and that was the slope of the tangent line to the curve. So at the point x equals 1, which was P1, we found that the tangent has a slope of 2. So we did indeed find exactly what we were looking for. And this is also called the derivative of a function at a point, and that's a very important word from calculus. And again, all we're referring to is the slope of the tangent line. So now that we know how to find the slope of a tangent line numerically and graphically, let's actually extend this concept and think a little bit more about how would we find the derivative, so the slope of the tangent, at every single point on the curve. What would happen if we did that? What would happen if we plotted it? What would that new function look like? In other words, how does the function describing the slope of a graph relate to the original graph itself? Well, let's go ahead and do an example. Here we've got y equals x squared, which is the parabola shown in red, and we want to go ahead and find the slope at a variety of points. So in doing that, we construct the table shown on the left, so we're finding the slopes of the tangent at various points, either numerically or graphically or whatever the method might be. But the idea is, if we were trying to find the slope of the tangent line at the point -2 on our curve, let's say we did that numerically, we would end up with a slope of -4. If we then tried to find the slope of the tangent at the point -1, again, either numerically or graphically, we'd end up with a slope of -2. If we tried to find the slope at x equals 0, it's pretty clear from the diagram it's a horizontal tangent, so we're going to get a slope of 0. If we try to find the slope at 1, we're going to end up with a slope of 2. And if we tried to find the slope at 2, we would end up with a slope of 4. So now let's have a look at the slope values that we found. At -2, we got a value of -4. At -1, we got a value of -2. At 0, we got a value of 0. At 1, we got a value of 2. And at 2, we got a value of 4. This kind of looks like a table of values for the line y equals 2x, because all we're doing to get the slope is really multiplying the x value by 2. Well, that's interesting. Let's go ahead and plot the points that we get from this table of values. Well, we're going to end up with this black line, which is indeed the line y equals 2x. So what does this mean? Well, what we're showing is that the black line here represents the slope of the red curve at each x value. So let's say we wanted to know the slope of the graph at -1.5. Well, what this means is we're looking for the slope of the function y equals x squared at -1.5. Now, according to this derivative function we found, all we would have to do is figure out where the line y equals 2x is, so what y value it has when x is -1.5. And we know, of course, that if y equals 2x and x is negative 1.5, y is going to be negative 3. So what we're saying then is the slope of the tangent of y equals x squared at negative 1.5 is 3. Again, if we're starting with the function y equals x squared and we find the tangent lines at every point along it, the function that describes those tangent lines is the function y equals 2x. So in other words, y equals 2x is the derivative of y equals x squared. So does that mean we're done? Have we figured out how to differentiate the function? Well, we haven't figured out how you get from y equals x squared to y equals 2x, and there's in fact many rules for helping us to do this, which we'll get to in just a moment. But let's describe this concept a little bit more. Differentiating a function means finding a new function, and we call it f prime of x, and it's got that little tick mark beside the f, the little apostrophe sort of. Here the way it's drawn actually looks like an apostrophe, but it's just a little tick mark, and the idea is it's called f prime x. It denotes the slope of the function f of x at every point. So from our previous example, if the function is f of x equals x squared, we can say that the derivative function f prime of x is 2x. Another way you might see that denoted, either by your professor or in your textbook, is through the notation d by dx out in front of the function. So d by dx of x squared is 2x. And what that d by dx means is, again, the process of differentiating, so finding the derivative. And now, how do we actually know this? Are we going to have to, each time, figure out at a whole bunch of points, numerically and graphically, what the slope of the tangent is going to be, and then look for a pattern, then try to figure out what function matches that? Well, luckily no, because this has been done before, and people have been able to work out patterns and do general proofs, and so we have lots of rules for differentiation that actually make it very easy to differentiate. For example, the simplest rule is something called the power rule, which tells us that the derivative of a power function, so x raised to some power n, is going to be n times x to the n minus 1. So in other words, you bring down the power and you reduce the power by 1. So that's exactly what we did in our previous example. We had x squared, we brought the 2 down in front, and we reduced the power by 1. So we ended up with 2 times x to the 1, which is just 2x. As another example, if we had f of x equal to, let's say, x to the 7, well, that would mean f prime x would be 7, you bring the power down, and you reduce the power by 1, so 7x to the 6th. And again, there are many rules for differentiation. There are rules called product rule and quotient rule and chain rule that are going to help you figure out how to deal with functions that are multiplied or divided or compositions of functions. That's beyond the scope of this video. This is just an introductory video to help you to understand what differentiation, the first branch of calculus, is all about. So what it means to find derivatives and why we do it. And again, what it tells us is it tells us the instantaneous rate of change of a function at a given time. So you know exactly how quickly something is changing at a given point on the graph. So now let's go on to the second branch of calculus, which is integration. And integration is the inverse process of differentiation. So one process undoes the other. For example, if we differentiate x squared, we already know that we get 2x. If you then integrate 2x, you'll get x squared again. And so, again, all we're doing is undoing the process of differentiation. We're asking ourselves, what function, if I were to differentiate it, would give me 2x? The answer is x squared. And in doing that, what I've really done is I found the antiderivative of 2x or the integral of 2x. Okay? So that means the same thing. There's things called indefinite integrals and definite integrals, a little beyond the scope of the video, but basically indefinite integrals don't have any numbers on the integral sign, and it's the same thing as an antiderivative, whereas definite integrals are going to have to do with the area concept, and we'll study that in just a minute. Just a word of notation though, the way you denote integration is whatever function you want to integrate, so 2x, you have to put a dx beside it. And it's not always going to be dx, it might be dt, it might be dy. The idea is the variable, it's always going to be a d, but the variable x is going to match the variable that's used in the function you're integrating. So here, because we have 2x, we have to write dx. If we were integrating 3t squared, for example, we would have 3t squared dt. And the other thing you have to do to show that you're integrating is to put this sort of elongated s out front, which is called an integral sign. And so again, what we're saying here is the integral of the function 2x is x squared. It's actually x squared plus a constant, so technically there's actually a plus c after the x squared, and that's because if you were to differentiate, because remember we said that integrals and derivatives undo one another. Well, if you were to differentiate this, you would end up with 2x. The thing is, x squared plus 7, for instance, well, 7 has a slope of 0. Think about the function y equals 7. It's just a horizontal line. Its slope is 0. So the derivative of any constant is 0, and that's why you can have an arbitrary constant on the end when you integrate something, because if you differentiate it, that arbitrary constant goes away. This is getting a little bit perhaps too advanced for an introductory video, so I'll leave it at that, and you'll learn much more about integration in the courses that you're studying. Again, this is just meant to be a basic video to introduce you to the concept in case you need it for another class that you're using integration in, such as physics, for example, but you haven't yet covered it in your calculus class, or you've covered it a while ago and you don't quite remember and you want a refresher. So again, this is the process of integration. It just undoes differentiation. And again, in terms of the notation, you need both the integral sign and the dx at the end. That's just how we denote that we're integrating. So what does this whole idea of integration have to do with area? Because in the first slide, we had said that integration is a problem of finding areas under curves. Well, this is where the idea of definite integrals come in. If you put actual bounds specifying an interval on the integral sign, what you're doing is actually finding an area under a curve, and that actually denotes the total change that occurs over the time interval. So that sounds a little bit confusing. Let's go back to this area problem. Let's say we wanted to find the area under the red curve shown here. How would we do it? Well, what we could do is break the interval up into several smaller pieces and approximate the area underneath the curve with rectangles, for example. Because we know how to find the area of rectangles, it's just the width times the height, so it's a lot easier for us. The width is just going to be some small little width that depends on taking the interval and dividing it into a certain number of pieces. In the diagram on the left, for instance, we've taken an interval of length 2 and we've divided it up into 5 pieces because we've got 1, 2, 3, and it's hard to see here, there's 4 and then a 5th rectangle. What you've got then is a length of 2 divided into 5 parts, so the width of each rectangle is 0.4. Now what about the height of the rectangle? Well, we can figure out where the rectangle touches the curve, and we have different ways of figuring out the height. We might look at where the rectangle touches the curve in its center, or perhaps where the right endpoint touches the curve, or the left endpoint of the rectangle touches the curve. So we might have different approaches. And in fact, if all we were doing is an approximation, as you might study later on in calculus, these are all different approximation techniques. But if all we're interested in is actually considering more and more rectangles, just like previously we considered for finding slopes, we had the point P1 and P2, and we brought P2 as close as we could to P1, and we saw what happened. Well, here if we consider more and more and more tiny rectangles, so as you can see in the diagram on the right, we're using more rectangles and they're a lot thinner. If we keep doing that, you'll notice that the area under the red curve is better and better approximated by the area of the green rectangles. So the approximation gets better and better. If we used 1,000 really, really thin rectangles, you can imagine that the approximation would get better and better and better, and we'd be able to approximate the area under the curve. So how are we finding area then? Well, again, the integral function, evaluated between two endpoints, gives us the area under a curve, and the notation that we use is the same notation that we used for integration before, but this is now something called a definite integral. And what makes it different than the one we saw before is it has these numbers at the top and bottom of it. And these denote the starting and ending value of where we're going to be finding the area under the curve. So here we're finding the area under the graph of 5x to the 4, as shown in the diagram, between the points 0 and 2. And if you were actually going to go ahead and figure out what this integral is equal to, in order to do that, you need to know a lot more calculus. So how we get an answer of 32. So you need something called the fundamental theorem of calculus. So I'll just write it as FTC for short to figure this out. So again, you need the fundamental theorem of calculus to understand how we got an answer of 32 here. This is not at all obvious. So again, when you continue with your study of calculus, you'll learn how to do an integral such as this one. It basically has to do with anti-differentiating 5x to the 4. So figuring out what function, if I differentiate it, will have a derivative of 5x to the 4. And if you think about that, when you differentiate, you bring a power down, reduce the power by 1. So since your new power is 4, that means the original was 5, and here it looks like you brought that 5 down. So in fact, if you think about it, the antiderivative of 5x to the 4 is x to the 5, because if you differentiate x to the 5, you get 5x to the 4. And then as for how to deal with the 2 and the 0, well, for reasons you'll learn when you study the fundamental theorem of calculus, all you have to do is substitute in the top limit and subtract what you get when you substitute in the bottom limit. So in other words, you get 2 to the 5 minus 0 to the 5, and that's how we got our answer of 32. And as for why this makes sense, well, again, that process is something you'll learn in your calculus course. And this video is just meant as an introduction. If you've forgotten calculus a little bit, or it's something you haven't studied and you're expected to know a little bit about it in one of your courses, again, the key point to understand is that there's two branches, differentiation and integration. Differentiation, you're finding derivatives, which is slope of tangent lines. So the slope of a function at a given point. That's all there is to it, and there's rules to help you do that. Integration, the second branch, is about finding the area under a curve. It's the opposite process of differentiation, and again, what it's telling you is the net change, the total change that takes place. So for instance, in this example that we just worked through, if 5x to the 4 was the rate of change of a population, and then 0 and 2 were times in years, we would know that the population changed by 32 in the first 2 years. So again, what it tells you is total change. So instantaneous rate of change is derivatives, and net change, so total change, is integrals. And those are the two branches of calculus. For examples, you'll find videos walking you through how to find derivatives and integrals or antiderivatives on this website. So you can go ahead and have a look at those to actually see the process in action.